So today we're going to do two things, I think. One is review chapter 12 on entropy and the Einstein model of a solid. And the second is I'd like to talk a little bit about curving motion, because that's been one of the things that's been tests. So basically, let's talk about how we got here. So the reason we got into talking about entropy was that we realized that there were some processes that didn't violate a fundamental principle but seemed never to occur. So, for example, when you put an ice cube in a cup of hot coffee, it wouldn't actually violate the energy principle to have the ice cube get colder and the coffee get hotter. Energy would still be conserved, but we never see that happen. Why not? If we put this chalk on the table, it could happen, wouldn't violate energy or momentum, that all the atoms in the table under the chalk are moving up at exactly the same time to give an impulse to the chalk so it jumps up into the air. But if we wait for a while and we watch the chalk, we just don't see that happen. Why not? And it led us to thinking about randomness at the microscopic level. And so the basic message of chapter 12 is that random motion, random exchange of energy occurs all the time, and entropy isn't some magic driving force. Entropy is just a measure of things becoming naturally more random. So randomness is, so the motion of these atoms in the table is very random, and it's just plain extremely improbable that all the atoms under the chalk would be moving up at the same time. Not impossible, but just improbable because the energy is so randomized in the table. Energy flow from one object to another by exchange of photons or through collisions depends on random processes, and so it's just extremely improbable that energy is going to flow from a hot thing to a cold thing. It's typically going to flow the other way. And we've been looking at microscopic models of this. So our context was the ball spring model of a solid, which we've been working with all semester. But we said we're going to make this model a little more idealized. And so we have in our ball spring model, we have atoms in 3D, of course, bonded to each other by covalent chemical bonds, and we model the atoms as little masses, little balls, and the chemical bonds are very spring-like, so this turns out to be a good model of a solid. And in this model, which was due to Einstein, we make the following idealization. We say that one atom, which can vibrate in either the X, the Y, or the Z, can be modeled as being three different quantum oscillators, one that oscillates in X, and one that oscillates in Y, and one that oscillates in Z. So that's part one. And furthermore, that each of these oscillators is completely independent from the others. So it's as if we kind of built walls around every atom like this. We said, okay, when this atom moves, it isn't going to affect this spring. So it's independent. And then we said, well, we know something about energy and we're an oscillator, is that's an oscillator, a mass on a spring. Well, we know something about the energy in tiny quantum oscillators, and oscillators that are really, really small. We know that the potential energy graph for an oscillator, so this is energy and this is separation, and this is the equilibrium separation, that possible values of k plus u, unlike a macroscopic mass spring oscillator like the one you used in the lab, possible values of k plus u have discrete values. You can't just have any old value of k plus u. So you could have k plus u could look like that, or it could look like that, or that, or that, but nothing in between. And that that there's a lowest possible value. This is called the ground state. And the way that an oscillator, a vibrating atom on a spring, can gain energy is it can absorb a photon of the right energy and go up to the next level, or if the photon had twice that amount of energy, it could go up 2 levels, okay? And it, conveniently for this quantized harmonic oscillator, this energy spacing delta E is a constant. So this energy is delta E, that energy is delta E, that energy is delta E. It makes our lives really simple in terms of this model. And this just falls out of the energy equations you solve to get this model in a quantum mechanical way. And it turned out that delta E, which we call 1 quantum of energy, can be calculated by as being the constant h bar times omega 0, which is h bar times the angular frequency at which this little ball and spring oscillate. And so this is, since this is a microscopic oscillator, this is the interatomic spring stiffness divided by the mass of one atom, since we're working entirely on the microscopic level. For the mass spring you used in the lab, that would be the spring stiffness you measured and the mass of whatever it was that you hung on the bottom of the, okay? And we have some constants. H bar is, this is pronounced H bar, and it's 1.05 times 10 to the minus 34, I think. Yes. Joule seconds. And we actually make a little adjustment to our model here because we want the interatomic spring stiffness in this model, and we used Young's modulus when we stretched a wire. We could get the stretchiness, Young's modulus. We can get the interatomic spring stiffness from that. But in that model, we were thinking about the whole spring. And in our little oscillator here, we've we've sort of drawn walls, we've built walls around each atom, basically. And we say, well, so what's this atom connect? We wrote down the equation, the net force on this atom. We'd want these spring forces at each time. But we have two springs. So the effective spring stiffness would be the interatomic spring stiffness we measured from Young's modulus. We need to multiply by 2 because that's the number of springs. But notice that each spring is only half as long. And remember, if we cut a spring in half, we double its stiffness because that piece will stretch only half as much. So really what we're going to use here is the effective interatomic spring stiffness, which is going to be a factor of 4 greater than what we measured from Young's modulus. Now, in the scheme of things, this isn't going to matter. This matters if you're actually trying to fit data to the model. If you're just trying to see the shape of what happens, it's not going to be a crucial piece. And then we said, well, let's assume randomness in distribution of energy. So let's imagine we have a lattice of lots and lots of atoms. And we have a certain amount of energy that we're going to put into this piece of material. And that amount of energy is going to distribute randomly among all the atoms, right? So we asked what we thought about. First of all, we said, how many ways are there of distributing energy among? So if we had number of ways of arranging Q quanta in N oscillators. So if we had one atom, a particle so if we have 3 oscillators, which is our model for one atom, which really isn't a piece of material at all because it's not bonded to anything, but just for a simple number. And we had 2 quanta of energy. We could put them both in here. So this would have 2 quanta, and this would have 0 and 0. Or we could put them both in here. And so we went through the list and figured out all the ways we could arrange it and added it up. And that gave us the number of ways of arranging it. And that got hard to do on our fingers real fast. So we found a combinatorial formula that worked. And so number of ways turned out to be, and this is called capital Greek omega. And it turned out to be Q plus n minus 1 factorial over Q factorial times n minus 1 factorial. And sometimes we can just do this on our calculators, and sometimes the factorials get too big and they overflow. And then we need to use a combinations function. In VPython, we would write this as omega is, the function's called combin, and the first argument would be Q plus n minus 1, and the second argument would just be Q. Q on your calculator, there's a thing called something like NCR, and you're either putting things, depending on what calculator you've got, these quantities go there. And the way those things work is they prevent numbers getting too big and overflowing the internal storage by just doing all the cancellations. So since q factorial is part of q plus n minus 1 factorial, that gets canceled out, and then it gets easier to compute. So it's just a computational trick to do that. And so if we considered, our argument about entropy and temperature involved considering putting two objects together and looking at the most probable distribution of energy. So like we did macroscopically, we do microscopically, we take two objects and we count the number of oscillators here and the number of oscillators, ways of arranging the amount of energy we've got here. And we got graphs of number of ways. So this is omega versus the number of quanta in object 1 that sort of looked like this. And this was the distribution we were going to see more often if we took 1,000,000 of these systems and put that amount of energy in them and let it slosh around for a while. Most often, if we took a picture, we'd see this one. But these are, and so this is sort of a probability distribution of and then we actually converted this graph into, we took a log, because when we got lots and lots of oscillators, the graphs started to look like that, and it was just kind of hard to see what was happening out here, so we took logs. And so if we took the log of omega versus q1, we got distributions that looked kind of like this. So this is block 1, and this would be block 2. And then if we added these two things together, we got the total. So the number of ways of arranging this was omega total was just omega 1 times omega 2, because for every arrangement here you had lots of arrangements, omega 2 arrangements here. So you had we're adding logs, so this just turns out to be log of omega 1 plus log of omega 2, and the most probable distribution was the max of those two things. And it turns out that if you multiply this log of omega 1 or log of omega 2 by the constant Kb, the Boltzmann constant, that turns out to be the entropy, which was a number that was derived independently before anyone knew about atoms. So a couple hundred years before that, by people who thought really, really hard about complicated things. So entropy, S, is the Boltzmann constant times the log of number of possible ways of arranging things. And the Boltzmann constant is 1.38 times 10 to the minus 23 joules per Kelvin. And from looking at this graph, we were able to come up with a relationship between entropy and temperature. In fact, we were able to come up with the actual physicsy definition of temperature. Because we said, so if we just multiply all this by everything by k sub b, this becomes entropy. So this is now S1 plus S2. We said, well, when the total entropy is a maximum, this is the most probable distribution. And the thing that's true when we get to this equilibrium distribution is that the temperature of these blocks is the same. The amount of energy in them isn't the same, but the temperature is the same. And so we said, well, notice that at this maximum here, the slope of ds dE, so this is S versus this. We multiplied S by Q1, but we can convert it to E just by multiplying by the number. This is the number of, if we multiply by the amount of energy in a quantum, then we get energy. So ds dE has to be 0 at the maximum. And that means that it said, well, then this slope and that slope have to be equal in magnitude and opposite in direction. So ds1, the amount of energy in block 1 is minus ds2 dE1. We're still going that way. But we can convert this into, so E1 goes that way, but on this graph, E2 goes that way. So when E1 is 0, E2 is all the energy, and when E1 is all the energy, E2 is 0, right? So we could say ds1 dE1 is equal to plus ds2 dE2. And it's probably not an accident that these slopes are then equal, because at equilibrium, something's equal between these things, and so those must be related to temperature. And we eventually ended up reasoning that that ds dE was actually equal to 1 over the temperature in Kelvin, because we have a big slope here when the temperature of this block is low, and a small slope when the temperature is high. So we got this relationship. It's really a partial derivative, but because we're holding volume constant. There's some other variables, but and so this allowed us to calculate the temperature of an object just by looking at the slope of the curve of change in entropy with respect to energy. And then we could take one step further if we have two values of temperature. So change in energy on a per something basis is delta T. And so delta E internal over delta T should give us the heat capacity per something. If it's for the whole block, that's called the specific heat, but then if we do it on a per atom or per gram or per mole basis, it becomes heat capacity. So what I thought it might be useful to do today, we did a little bit of this in recitation, but I don't know how many people actually finished, is to just go through this calculation all the way for one object, and just see the relationships build up. So that's what we're going to do. So we're going to consider a nanoparticle of lead, which is a very soft substance. So it's got a very, so lead, the atomic mass is 207 grams per mole. And if you make Young's modulus measurements, you get an interatomic spring stiffness of is about 5 newtons per meter, so they're very soft springs. It's not a good idea to handle lead, but if you've ever done it, maybe with gloves on, you find you can bend a sheet of lead very easily. It's a very malleable substance. So what we're going to do is consider a nanoparticle that has 15 atoms, say, and 10 quanta of energy, and what we want to find out eventually is the heat capacity per atom in that situation. And interestingly enough, we now have enough information to do that by using our model. So the first thing to figure out is well, okay, it's not the first thing, so we won't do it first. So the first thing to do is to say, well, how are we going to do this? So we need a plan. And our plan is this. Since heat capacity is going to be delta E over delta T, we're going to need to know delta E. Now, what is this delta E thing? Okay, we'll think about that for a minute. But so what we need here is we're going to need two values of temperature because we're going to have a delta T, right? So basically, we're going to need a T higher and a T lower so we can get a delta T. Well, temperature, if 1 over T is delta, approximately delta S over E, then T we're going to approximate by delta E over delta S. So that looks like we need two values of S for that delta T, but then we're going to need two values of S for this delta T. We can use this one again. So we're actually going to need 3 values of S. And what do these 3 values of S correspond to? Well, they correspond to different amounts of energy in the system. Okay, so if we want to get the temperature at around quanta, that means we better do 9 and 11 also in order to get this. And that comes, of course, from getting the number of ways of arranging the energy, so we better start with that. So let's try to make a table that we can fill in with our calculations. And maybe before we do that, we better figure out what this delta E thing is, because we're going to need it. Oops. Escaping chalk. It's very small anyway.
Isn't the 11 on top?
It would be. The 11 would be on top. Put high temperature on top. That's probably a better idea to be consistent. Okay. So what is this delta E thing? Well, if we're going from putting 9 quanta in a system to putting 10 quanta in a system, it better be the amount of energy in one quantum, right? So how do we figure this out? So delta E is equal to H bar.
Square root of KSI.
Okay, we're going to say it's over the mass of an atom. And so now we need to do some calculations. So
Is it always going to be 4 times?
well, is it always going to be 4 times? Yeah, because in our model, remember, we have an oscillator. We're thinking about an X oscillator or something, and so there are 2 springs, but each one is half as long. So, okay, so H bar is what did I say? 5 times 10 to the minus 34. And KSI was 5 newtons per meter, and the molar mass of lead 207 kilograms, and Avogadro's number is 6.02 times 10 to the 23rd. So delta E to H bar, square root of 4 times KSI divided by the molar mass of lead divided by Avogadro's number. So if we run that, it seems to be 8 times 10 to the minus 22 joules, right? So that's the amount of energy just to go from the ground state to the first excited state, or the first excited state to the second, or whatever, yeah.
Okay. I'm just kind of confused why delta E would be from like to 11.
Well, we want to know what the temperature is when we want to know what the heat capacity is when it's got about 10 quanta of energy. But we could calculate the entropy there, but then we can't go any further because you need 2 values of entropy to get a temperature. So we better look at 9 to 10 to get this low temperature. But then we need another value of temperature. So we go from 10 to 11 to get the other value of the temperature. So we're really going to need 3 different values of energy to get, because we're taking derivatives here. So there's nothing that our equations are expressed in terms of derivatives, so we need some differences. Other questions? Okay. So now let's see what we're going to need. We're going to need, for every value of Q, we're going to need the number of ways of arranging that amount of energy in the number of oscillators we've got. And then we're going to need the entropy. And from there, we want to get a temperature and then eventually a heat capacity. So we want to start with that many quanta, and we need to calculate the entropy of our little nanoparticle for having that much energy in it. Right? Okay. So we're going to need another constant. Let's put it up here. The Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin. So now let's, and how many oscillators do we have in this model? We have n atoms. Let's see, we've got n atoms. What did we say? 15 atoms? 15 atoms. Okay. So how many oscillators do we have? 45. So n is n atoms times 3 because we're modeling each atom as 3 independent oscillators. Okay, so we'll say Q is 9. There. And omega is the number of ways Q plus n minus okay, and now we need Q equals, you can just because it's the same, and now we need Q equals 11, and the calculation is still and we'd write a loop. So I think we're okay. Call this omega 10, and we'll call this one omega, whoops, let's call it omega 9. Omega 9, omega 10, omega 11. And so we're going to print omega 9, omega 10, omega 11. So they're big numbers. We have 4.43 times 10 to the 9th, 2.39 times 10th, and 1.1, well, really 1.2. 1.2 times 10 to the 11th. So you put a little more, put one more quantum in, and you have a lot more ways of arranging the energy. Okay, so stop me if something's unclear at this point. Let's calculate the entropy at each. So S9 is just KB times log omega 9. And notice that in Python, log means natural log. Okay, so this is not a log base 10. If you wanted a log base 10, you have to say log 10. So this is, and so I'll make this S10, and yes.
Where did NA come from? That looks like Avogadro's number.
That's Avogadro's number. We use that because when we're calculating, and so we know that a mole of lead atoms weighs 0.207 kilograms, but we need the mass of one atom, so we have to divide by Avogadro's number. That make sense? Okay. Here. Okay, so we have 3.07 times 10 to the minus 22. Whoops, that's the wrong place. It's down here. 3.07 e minus 22. 3.30 e minus 22. 3.2 e minus 22. And the units must be joules per Kelvin, because those are the units of the Boltzmann constant.
So does omega have any units assigned to it, or is it just a number?
Oh, omega. So what? No, this capital omega. It's the number of ways of arranging things, so it's just a number, right? Because at first you count it on your fingers to, yeah. Okay. So now we've got the entropy for 3 different amounts of energy, but now we have to get a temperature. So since temperature is, we can approximate it by delta S over delta E. If we combine these two values of entropy, we ought to be able to get a temperature, right? So T low, we'll call it, is, so delta S, what's delta S going to be? S10 minus S9 divided by, and here's where our delta E comes in, right? And T high is equal to S11 minus S10 divided by dE.
S9 is the capital S.
What? Yes.
Why are we doing ds over dE if the temperature is dE over dS?
Oh, good point. Let's do it the other way. That's 1 over temperature, so Okay. So if we did this right, then our first value should be lower than our second. This temperature is 34.4, and that temperature is 36.1. And what are the units here? These are Kelvin, right? So these are real Kelvin temperatures. Okay, so we have one more step, right? So the heat capacity of the whole thing is going to be equal to what? Okay, so delta E over T high minus T low, or phi. And then on a per atom basis, is C divided by the number of atoms, right? Because so if we print C, that's our heat capacity, and if we print C per atom, that's so we find that for the whole thing it's 4.87 times 10 to the minus 22 joules per Kelvin, but C per atom is equal to 3.24 or 25 times 10 to the minus 23 joules per Kelvin. Yeah, that's exactly right. That's what computers are good for. You don't have to.
We don't have to.
That's right.
But you get that button.
Now, at a temperature, at sort of the room temperature limit, it turns out that the heat capacity of most metals on a per atom basis is around 3 times the Boltzmann constant. So let's just print 3 times Kb to see what that would come out to. And that comes out to 4.14 times 10 to the minus 23rd. So it's clear we're not there yet, and that makes sense because we're down at 36 Kelvin. So, and if we plot, if we make a graph of heat capacity versus temperature, so if this is T, and that's C, what you find is kind of looks like that. Yeah.
So why does it take at lower temperatures less energy to warm something up?
So what? So why does it take? So the question is, at low, physically, why is it? Can we think about this sort of intuitively? Why does it take smaller energy input to get a bigger increase in temperature at lower energies, at lower temperatures? And I think the best answer I can give, but you should think about it, is that when we have lower temperatures, we're talking about lower amounts of energy, so there's fewer ways to arrange it. So the amount of randomness is actually much smaller than it is when you're up here and there's lots of energy and lots of ways to arrange it. That's people were really very surprised by this. People knew about that, but they didn't know about this until the beginning of the 20th century, when people started building really great refrigerators and getting down to low temperatures, and then they went, oh my goodness, we didn't know about this, what's going on? So yeah.
So does it go the other way? Does it take less energy to make stuff colder?
We have to take energy out to make things colder, right? It's very difficult to make things cold. You need to engineer ways to get rid of energy. All right, questions about this? You can't have a question. Yes, Flavio. At lower temperatures, there's less energy, so there are fewer ways to arrange it. But it's because there's less energy. The number of oscillators is still the same, right? So that's a constant. It's just that when you've got, if you had 21 oscillators and one quantum of energy, there'd only be 21 ways to arrange it, right? But if you had two quanta of energy, there's a lot more ways to arrange it. So at lower temperatures, there's less energy, so therefore there are fewer ways to arrange it.
And then if you add energy when it's cold, that's why you get that. Like, instead of like small energy, you see spike.
Yeah, so I mean, even a small amount of energy means that there's, so we put in one quantum, which is a really tiny amount, 10 to the minus 22 joules, and we get an order of magnitude more ways, so 10 more ways to arrange it, another 10, you know, so it's a big effect. And I think it's actually useful to see the numbers, to see this happen. Yes, no.
And in response to the question about trying to get really, really cold, you need something even colder than the thing that you're trying to cool down in order to get energy to go out of this even colder thing. So it's hard to get something cold, and this heat thing to cool something else, that's another problem. And if you look at that graph, and you think not about the thing you're trying to cool down, but the heat sink that you're trying to use to get that, this heat sink has a very low heat capacity. So just a little bit of energy taken out of this thing is going to make its temperature go up too easily because it's got such a low heat capacity. So that's the fundamental problem of cooling things at a low temperature. You need something even cooler, and that really cooler thing has a very low heat capacity, and any little bit of energy coming in from the thing you're trying to cool is going to raise its temperature. So you're screwed.
Solution, just use ice.
Just use ice. Well, you need a particularly special kind of ice to get down near 0 Kelvin. But ice. Ice. All right. The other thing, do you have any other questions about this? So the other thing I wanted to talk about briefly, because this is a thing that's shown up as a difficulty on tests, is curving motion. It turns out that there's something about curving motion that hits all of our instincts the wrong way. So our intuitions are typically just wrong, and we actually have to check them by using physics, and if we don't, we get into trouble. So remember that we can write the force acting on something as the sum of a force that's parallel to the momentum and another force that's perpendicular to the momentum. Usually we just say parallel and perpendicular, and you're supposed to know that we're talking about the momentum. So here's P, there's F, And we can write this as F is the sum. Let's make our lives simpler. Here's F. So F we could write as having two components. One component that's in the direction of the momentum, so it has to go this way. And then one component that's perpendicular to that. And this is useful because it's this component momentum, and it's this component that makes its magnitude bigger or smaller. So and because you can write forces this way, you can also write dp dt this way. So dp dt has two components, a parallel one and perpendicular to the momentum. And so dp dt d parallel is equal to f parallel, dt perpendicular is equal to. So that's all fine. We break down a little when we try to actually apply this. So let's just think of it's a pretty light line, but you can probably see it. So consider location E. Let's think about how we would draw F parallel and F perpendicular in this situation. So here's our star. Here's a comet. We're here. Now, there are a number of ways to think about this, right? So first of all, what's the answer to the question? Yeah, 4 is correct. Neither one is. And I mean, how do we know that neither one is 0? So it's the magnitude, so its velocity is changing both in magnitude and in direction. So, okay. So how would we draw, so how would we draw dp dt here? What's the direction of dp dt? Okay, so yes. So this is actually really important. We have a procedure for finding dp dt, and we need to use it. So we take 2 points bracketing this location, and we draw the momentum at each location, right? So let's take here, and I draw the momentum. Yeah, so tangent, so we've got, so now we've got one here, and how do I draw the momentum? Smaller, it's slowing down, so let's draw it. So P final, we'll call this P initial. Now we draw these things tail to tail, so we and delta P which way does delta P go? Okay, so it's final minus initial. And so the direction of dp dt is the same as the direction of delta P over delta T, of course. And so dp dt is going to look like that. Now we have a way of checking that, right? What's the way of checking to see if it makes sense?
Create a solar system.
Create a solar system and see if it works that way. That's one possibility. The other is just to look at the direction of the force acting on the comet, which of course is a gravitational force due to the star. And so the force had better be pointing in that direction from the comet to the star. So the direction of dp dt ought to be the same as the direction of f. If you know the direction of f, that's certainly a way to check it, right? And so one thing to note here, here's our momentum at this point. The quote parallel component of dp dt. What's the direction of dp dt parallel at this instant? So let's clean up this diagram. Here's the momentum. If I said draw the parallel component of dp dt, how would you draw it? All right, this is a key point. So what does it mean? How do we draw it? So it's got to be somewhere along that line. But there are two possibilities. It could point this way or it could point that way along that line. Which way does it point? Yeah. So the parallel component and it's acting to slow down the momentum, right? So opposite to the momentum. So now do we find dp dt perpendicular? It's got dp dt parallel and dp dt perpendicular have to add up to dp dt, right? So it's going to be so it's going to be I knew that. So by parallel, it just means along the line of momentum. It doesn't mean it has to be increasing the momentum. It could be decreasing them. How do we calculate it numerically? You did this, but you may not remember. Or well, actually, you did it with force, not. So since you did it with force, let's talk about force. Suppose we have, you did this in labs, so it's not, suppose we have momentum this way and a force that way. And the momentum is minus 400 kilogram meters per second, and the force is 3 minus 50 newtons. Do you remember how to get the F parallel and F perpendicular? So the magnitude of F parallel is the dot product of the force and the unit vector in the direction of momentum. So what's p hat here? Yeah. Negative 1, 0, 0. One of these things we can do by inspection. So this is 3, negative 5, 0, dot, negative 1, 0, 0. And this is a dot product, not a cross product. So it's 3 times negative 1 plus negative 5 times 0. So that gives us a negative 3. So therefore F parallel is going to be a negative 3 times p hat. So we get 300 newtons. So this is the parallel component of F. And the perpendicular component of F you would get by, yeah. So F perpendicular is F minus F parallel, which should give us 0, negative 5, 0 newtons. So it's a very concrete thing. Yes. What? Oh, you weren't here last time. Out of town next week. I have to give a talk in Oslo, so I'm flying to Norway tomorrow. So.
Wait, you're part of Norway?
Yeah.
Where Norway?
Oslo. Yes.
Justice and Sage.
Yep, Justice and Sage.
What's the topic?
What's the topic? Wow.
She's teaching history.
Yeah, so someone else had a question here, though. No?
No, we're interested
You're interested.
in what you're going to be talking about, and we're going to find it on the internet.
Give us a 7-minute summary of your entire speech.
I'm talking about integrating computation into introductory physics, computational modeling into introductory physics.
Crash course in that.
And you could come and help me give the talk.
Buy a ticket to Norway. Skip all of my exams.
Yes. Yeah, so one of the virtues of being an academic is that you do get invited to give talks in interesting places and people pay for your plane fare. So, so that's all right. So last question and then we'll quit. What's the direction? This is at constant speed, okay? So the particle's traveling this path at constant speed. So, what's the direction of dp dt? Remember, we have a procedure.
Because that spot should be bigger and greater.
Remember, the speed is constant. Speed is constant, so okay, what's the answer, guys? Whoa. Well,
We tried very hard.
okay. So over here we have a lobby. Okay, we better do it. I think we better work this out. Okay, so okay, so that's the other way? Okay, we'll do it the other way.
Well, I would assume it was going from A to B, considering that there's the arrow, and I don't think that way. You know, we're talking about this. Because it rhymes with well, Mighty, you know what, I was right.
Okay. Keep breathing. Do well in the final. It's been a great semester. Thanks.